So we're going to talk about a piece of pure genius that quietly, almost invisibly, powers so much of our digital world. It's this beautiful, powerful, and surprisingly simple set of rules for finding the absolute best way to get from point A to point B. Okay, let's just dive right in.
I mean, really think about it for a second. Every single time you pull up a Maps app, you're basically asking it this age-old question: what's the quickest route? And that app, it chews through traffic, road closures, dozens of possibilities, and then, boom, in seconds, it spits out the perfect path. How on earth does it do that? Well, the secret sauce, in a lot of cases, is an algorithm that was dreamed up more than half a century ago.
All right, to get how a computer tackles this, we first have to, stop seeing a map as a picture. We need to see it as a puzzle. We have to translate our real, messy world into a language a machine can actually work with. And that language, it's the language of graphs. So let's imagine we strip a map down to its bare bones. Forget the street names, the buildings, all of it. Every place you can make a choice, like an intersection, that just becomes a dot. And every road that connects two of those dots, that's just a line. But it's a special line because it's got a number attached to it. And that number is how long it takes to travel that road.
And what we've just described is what folks in computer science call a graph. The intersections, those are the nodes. The roads connecting them are the edges. And that travel time on each road, that's its weight. Suddenly our problem isn't find the fastest route anymore. Now it's find the path through this puzzle with the lowest total weight. See how that reframes everything?
Okay, so you've got the puzzle. How do you solve it? We have to go back to 1956, to a Dutch computer scientist named Dijkstra. He came up with this totally revolutionary way to do it. It's often called a greedy algorithm, and its real brilliance is just how focused and logical it is, one step at a time.
Now, when we say greedy, we don't mean selfish. It's more like optimistic. The algorithm works by always, and I mean always, making the choice that looks like the absolute best one right at that moment, without even thinking about the big picture just yet. It's all about making the best local decision again and again.
And this is the key. This is the whole thing in a nutshell. The algorithm just expands outward from where you start, but it's not random. At every single step, it asks one simple question. Of all the places I know about but haven't locked in yet, which one is the absolute closest to my starting line? And then it goes there. That's it. That is the core idea.
Now that might sound a little bit abstract. I get it. So let's make it real. We're going to walk through a super simple example and watch this greedy idea in action. You'll get to see exactly how it builds the fastest route, piece by piece.
So here are the 4 rules of the game. First, we set up the board. Our starting point is distance 0, everywhere else is infinity because we don't know how to get there yet. Second, we always pick the closest place we haven't visited. Third, from there, we look at its neighbors and see if we found a new, shorter way to them. And fourth, we just repeat that loop over and over until we get where we're going. Let's see it play out.
Okay, here we go. Here's our little map. We want to get from city A to city D. So, for the setup, we say the time it takes to get from A to A is, 0. For every other city on the map, B, C, and D, the travel time is basically a giant question mark. We'll call it infinity for now.
All right, first move. We're at our starting point, A. We look around at the places we can get to directly. And we see we can get to City B in just 1 minute. We can also get to City C in 4 minutes. Simple enough. We jot those times down and we check City A off our list. It's now been visited.
Now, this is where the magic happens. We look at our list of places we can go. Which one's closest? City B, at only 1 minute away. So we visit B. From B, we look at its neighbors, and we spot a road to City C that takes 2 minutes. Now hang on, the total time to get from A to C through B is just 1 plus 2, which equals 3. Hey, that's better than the 4-minute direct route we found earlier. So we update our list. The best way to get to C is now 3 minutes. This is the algorithm correcting itself as it learns more. It's so cool.
So, what's next? The closest unvisited city is now C, with that new, shiny travel time of 3 minutes. So we go there. And from C, we can finally see our destination, D. It's just 1 more minute away. So, the total path we just took, A to B to C to D, adds up to 1 plus 2 plus 1, for a grand total of 4 minutes. This is the best route we've found to D so far, so we update our table 1 more time. The shortest known distance to D is now 4. And just like that, we're there.
Since D was our final destination, the algorithm can just stop. It has methodically explored, it's updated its knowledge as it went, and it has absolutely guaranteed that the path it found, A to B to C to D, is the fastest way to get there. The final answer is 4 minutes.
But here's the thing. This isn't just for finding your way to the grocery store. This same logic of nodes and edges and weights can represent all kinds of networks. And because of that, this simple idea has become a bedrock of modern tech, humming away silently in the background of our lives.
I mean, every time a little packet of data zips across the internet, routing protocols are using this logic to find the most efficient path. When a robot is trying to navigate a chaotic warehouse, or an AI character is figuring out how to move in a video game, it's often a version of Dijkstra's algorithm doing the hard work. It's even used to find the best series of connecting flights to get you across the world.
Now, the algorithm does have one huge, non-negotiable rule. All the weights, the travel times, they have to be positive. You can't have a road that lets you go back in time. If you had a path with a negative travel time, the algorithm would get stuck in a loop forever, just trying to take that time travel path over and over to get an infinitely fast route. So, for those weird problems that do have negative weights, there are other tools, like something called the Bellman-Ford algorithm. Bellman-Ford can handle those tricky situations, but here's the trade-off. It's a lot slower. It's really that classic case of picking the right tool for the job. Dijkstra's is the super fast, super efficient specialist, as long as you promise not to break the laws of physics. Maybe the coolest part of this whole story is how this world-changing algorithm was even created. It wasn't the result of years of grinding away in a research lab. Nope, it was a flash of insight, and it was born out of a need for things to just be simple. And these are Dijkstra's own words. He was trying to figure out how to show off what a new computer could do, but to people who weren't tech experts. He needed a problem and a solution that just made intuitive sense. And by forcing himself to solve it without any pencil or paper, he had to find the cleanest, most elegant path to the answer.
So you can just picture the scene, right? A morning shopping trip in Amsterdam. He and his fiancée are tired. They sit down for a cup of coffee on a cafe terrace. And in that moment of rest, he just mentally maps out the entire logic that would go on to route our data, guide our cars, and become a huge part of his legacy. It really makes you wonder, doesn't it? If you took a really complex problem in your own life and just stripped away all the unnecessary junk, what simple, powerful rules might be hiding underneath? What big puzzles are we all facing that maybe just need a moment of clear thought on a cafe terrace?